First semester calculus is focused on the problem of how to find the slope of a curve, even if the curve isn't linear. We learned to call a function that gives us the slope of a curve the derivative. We said to find a derivative is to differentiate, and we have this name now that we sometimes give to first semester calculus based on those words. We call it differential calculus. The calculus of finding derivatives and then using them in whatever useful ways you might use derivatives. One of the things that we learned is that if we didn't have a function to actually find a numerical derivative of, we can approximate the derivative by finding the slope of the secant line. Slope of the secant line. That's f of b minus f of a all over b minus a. Which we also call our average rate of change. So I want to draw this comparison to what we're going to do second semester. Second semester is all about finding an area under a curve. And we call this part of calculus integral calculus because we're going to learn integral calculus. Because we're going to learn about a symbol that's called an integral. And we're going to talk about how integral calculus, finding areas under a curve, is related to differential calculus, finding the slope of a curve. When the original founders of calculus they were just two separate problems that they were working on. They had no idea that these two problems were related. Well, it turns out they're related in a very exciting way, and that's going to be what we explore for second semester in our study of integral calculus. But to get started, we need to start to explore, what if we don't know how to find the area under a curve? What if the curve is so complicated and we can't actually find the area? How could we approximate it? So that's the discussion we're going to have here in 5.1, estimating with finite sum. So making an estimate of the area under a curve when we aren't able to find or don't have enough information to find an exact answer. You'll recall from geometry that you can take a larger area and split it up into smaller pieces. You could find the areas of those smaller pieces and add them up, you'd get the area of the whole. We're going to use a similar idea. We won't be able to find an exact area, and we won't have any geometry shapes that we'll be able to break the pieces up into, but we'll use an estimate based on trying to fill in those areas with, most commonly, rectangles and trapezoids. Well, that's our discussion here in 5.1. How can you use rectangles or trapezoids to estimate the area under a curve? So we're going to spend chapter 5 finding areas under curves. 5.1 is about how to estimate that area if we won't be able to get an exact answer. The rest of chapter 5 is about how to get an exact answer. But before we talk about how to get either an estimate or an exact answer, let's talk about why anybody would care to find the area under a curve. So go back to this problem that you've been doing for a long time. What if you have a train, it's going 75 miles an hour. How far does it travel between 7 a.m. and 9 a.m.? You can answer this by using this formula you probably memorized somewhere back in grade school. Distance is rate times time. So you figure out how long the train drives, the time that the train spends driving. 7 a.m. minus 9 a.m. minus 7 a.m. makes 2 hours. And you can multiply 75 miles an hour times 2 hours. And notice that the units even work right, because the units miles per hour multiplied by hours, the hours cancel out and give us distance, which is measured in this case in miles. So pretty easy problem. You have to make sure you think about the units. We checked that our units made sense here. But the thing is, in the real world, how often does something travel at a constant speed? So we want to start to try to figure out, can I figure out how far something goes if its rate isn't constant? So if you'll notice that picture on the page, that's page 263. If you look at that figure 5.1, that's a graph you could use to understand the train problem a little bit. You know the rate at which the train is going, and that's 75 miles an hour. It doesn't change, which is why it's a horizontal graph. And if you think about the math you did, the 2 hours, which is the time the train travels, multiplied by the 75 miles per hour, which is the speed at which the train is traveling, you you exactly found the area of the rectangle that's shaded in blue there. So the early discoverers of calculus were wondering, if I don't know that the speed is constant, does the distance traveled still represent the area under the velocity curve? So it turns out that it does, which set off in motion a whole pursuit of trying to figure out how to use algebraic methods to find the area under a curve if the geometry of the curve is not a geometry we already know areas for. Most important fact to take away from this video, I call it important area under curves fact number 1. If the velocity is not negative, then the area under the velocity curve gives distance traveled. You have to make sure that you think about the units. Remember when we multiplied rate times time to get distance? We had to have the units match up. So in the case of the train, miles per hour got multiplied by units of hours, so the hours would cancel. So as long as you've checked the units, and the units are going to work out right, area and the velocity must be positive. As long as those two things are true, you're going to find area under a velocity curve to find distance traveled over that time period. So before we even worry about estimating, let's talk about the times where we can easily find an exact answer using geometry we already know. So here I have an example. I have a car with a velocity that is not constant. This car is moving at 3/5 t plus 4 miles per minute for time 0 to 5. How far does the car travel during that time? Well, I'm going to start with a graph of this velocity function. I can look at this velocity function here and be clear that it's linear because the degree of the variable, the highest degree, is 1. So I know if I graph this, it's going to look like a line. I'm going to start by finding the y-intercept, which is going to have to be 1, 2, 3, 4 minutes. I'm going to use the slope up 3, 1, 2, 3 over 5. Here's my graph of the velocity curve. And I've been asked, how far does the, whatever it is, travel from time 0 to time 5? So I come to my graph and I know important velocity fact number 1, important area under curves fact number 1. If this is time 0 and this is time 5, I'm going to try to find the area under this curve between time 0 and 5. So I shaded that in yellow, and I can tell from my geometry experience that that's a trapezoid. So I can answer this question with no calculus, as long as I know that area under curves fact, but finding the area of that trapezoid, I just shaded in yellow. So a quick reminder, areas of trapezoids. Trapezoids, in geometry, most of the time you saw them, and they had bases that were parallel and horizontal. Most of the time in calculus, we're going to find that the horizontal sides, the parallel sides are vertical. But in any case, to find the area of a trapezoid, take the average of the two parallel sides and multiply by the distance across the other dimension. So that's what I'm going to do here. My two parallel sides, here and here. So this is going to be, that's a height of 4. This height is 7. To find the average, we add and divide by 2. So 4 plus 7 divided by 2, that's the average of the two bases, and then the distance across the other dimension. In this case, the distance between 0 and 5, which is 5. I'm going to multiply. So I know that, and I know my units on velocity were miles per minute. And I know my time is measured in minutes. So I'm going to multiply 4 plus 7 over 2 times 5 is going to make 55 over 2. Miles per minute times minutes simplifies to miles. Final answer. So let's find this next distance traveled. I have a particle traveling velocity v of t is square root of 16 minus t squared centimeters per second for time 0 to 4 seconds. How far does the particle travel in that time? Well, to find distance traveled, I need to find the area under the velocity curve. And in fact, between time 0 and 4, velocity is positive. To help you know, I recognize